Let's look now at section 9.5, and let's talk about alternating series. In this section, we're going to talk about a very particular kind of series. The alternating series is one whose name kind of gives away its nature. It's going to alternate back and forth between positive and negative terms. So for the alternating series, we're going to start off with a definition of what exactly we mean by that. Definition. Okay. Let's begin with a set of terms, the nth term of which must be positive. And you say, well, I thought you said it was going to alternate plus and minus. It will, but we'll take care of that separately. So let a sub n, the nth term of some sequence, we haven't made a series yet, we're still dealing with a sequence, let the a nth term be strictly positive. Okay? Then, when we say an alternating series, we mean the following. The sum, as n goes from 1 to infinity, of negative 1 to the power n times an, or the sum as n goes from 1 to infinity of minus 1 to the n plus 1 of an, is an alternating series. Okay. Here, notice if you have n to the first power, that's negative 1. If you have n to the second power, that's positive 1. N to the third is negative 1, and then positive, negative, and positive. Since these are always positive, that means that the sign change will be attributed only to this factor. So here, this really is starting from a negative number plus a positive number plus a negative plus a positive and so forth. Here, this is the same thing except it starts with a positive. Because notice if n is equal to 1, 1 plus 1 is 2, and negative 1 to the second power is positive. So here our first term is a negative, whereas here our first term is a positive. All this is saying is either one qualifies. You can have alternating terms that either start with a negative or alternating terms that start with a positive. If you take these alternating terms and add them all together, they form what's called an alternating series. So an alternating series on its own converges if and only if we have a very simple collection of statements, a very simple collection of conditions. So this brings us to a theorem. So let's begin with an alternating series. Let's have the same notation that we saw just a moment ago. Let a sub n be greater than 0. And let, let's just call this S be an alternating series. So one of these, and it doesn't matter which one. Let that be an alternating series. Okay. These series, either one, will converge when we have the following two conditions. S will converge if the following two things are true. One, we do need the limit of these terms to approach 0. So the limit as n approaches infinity of the a sub n term. That doesn't include that plus or minus, although we'll see in a moment that even if it did include it, it wouldn't really matter. We have our a sub n. This part is going to approach 0. And it has to not only approach 0, it has to be decreasing for all values of n. So here we have the limit, not the limit. We have that our a sub n plus 1 should be less than or equal to our a sub n for all values of n. So the proof of this, let's begin with an alternating series, but we're going to go ahead and limit ourselves to looking at the series, the partial sums with an even number of terms. That limitation won't last very long, but we're going to start with that. So let's consider the series, and here I'm just going to go ahead and pick one of these, but it doesn't really matter. It would work the same either way, because after all, if this one starts with a minus and this one starts with a plus, if you just cut off the first term of this one, it'll look like this one. And since cutting off a single term doesn't change whether or not something converges. If this is infinite, cutting off one term won't suddenly make it converge. And if this converges, cutting off a single term makes it smaller, not bigger, so it won't converge. Sorry, it won't diverge. So here, it doesn't really matter which one I look at, so I'm going to go ahead and look at this one, mostly because it'll make my notation look a little nicer here. So here, consider, and again, without loss of generality, we could use just this one, and whatever happens to this one will also apply to one that looks like this. Consider the sum as n goes from 1 to infinity of -1 to the n plus 1 times a to the n, or a sub n, like that. Let's go ahead and write out a few terms. So consider that series. Now consider the 2nth partial sum. When we say 2nth, what we mean is the first partial sum is the sum of the first term. The second partial sum is the sum of the first two terms. The fifth partial sum would be the sum of the first five terms. When we say the 2nth partial sum, we mean take an even number. Now, you'll remember from a previous section, 2n is just a generic way of writing an even number. So here we're saying consider a partial sum. We don't care which one you consider, but just make sure it's an even one. Okay? So if you consider the 2nth partial sum of this alternating series, we can go ahead and write it out the long way. So we'll write this as s sub 2n is equal to, and here, since I've chosen this one, we're going to start with the positives. After all, if n is equal to 1, 1 plus 1 is 2, and negative 1 to the 2 is positive 1. So our very first term will be positive. So it's going to be a1, and then our next one will be negative. So that'll be minus a2, and then plus a3, minus a4, plus a5, minus a6, and so forth. Now here we have an even we have a 2nth partial sum, the partial sum with an even number of terms. So every one will have a partner. All right? So here I'm going to say plus dot dot dot, and eventually we're going to get to a sub 2n minus 1 minus a sub 2n. All right? Notice the even ones are always the ones that are being subtracted. The odd ones are always the ones that are positive. So here the odd one is positive and the even one is being subtracted. All right? So now, this is a finite sum. It's just I'm adding some numbers. So the usual rules of addition and subtraction apply. As long as this is just a regular old sum, associativity applies. I can add things together in any order and in any grouping I like. So here I'm going to go ahead and write this as a sub 1 minus a sub 2. And then I'm going to say plus, and then I'm going to group these together. So plus a sub 3 minus a sub 4, plus a sub 5 minus a sub 6, plus dot dot dot. And eventually I'm going to get to a sub 2n minus 1 minus a sub 2n, just like that. Okay? Notice that this is a sum. Okay? Notice that here, these two, when I subtract them, they have to be positive. Why? Because my sum is decreasing. So the next term has to be less than the previous term, which means this is less than this, and if you take a bigger number minus a smaller number, it must be positive. All right, so right here, I'm going to go ahead and grab a different color for notations. Here, this, since we know, based off of this condition, that's why we need this as one of our conditions, since a sub 2 is less than a sub 1, then we know that a1 minus a2 must be positive. Okay? If you're subtracting something that's smaller, well, then there must be something left over, so that's got to be positive. And the same thing will be true for this one. Since a sub 3, I guess I should write that with the same pattern. Since a sub 4 is less than a sub 3, that means a sub 3 minus a sub 4 is greater than 0. And that'll be true for all of these until you get to the last one, in which case you can say since a sub 2n is less than a sub 2n minus 1, well then by subtracting these, I get something that's positive. Okay? All right, so what? Well, notice that if I were to add another term, I would be adding a positive number. every time I take another pair of these terms and add them together, I'm making this sum a little bit bigger, right? This will always be positive, and if I have a positive plus a positive plus a positive, every time I add a positive number, it's going to be getting a little bigger. So what that means is that the sequence, or let me write it this way. So the partial sum S of 2n plus 1 like this, if I go to add one more term, or in this case, I guess one more pair of terms, since we're looking at these with even number of terms. If I add another term here, that's going to give me something bigger than if I just kept this number of terms. So S sub 2 times n plus 1 is greater than S of 2n. But by definition, that means that our sequence is increasing. Every term of the sequence of partial sums is bigger than the one before it. Because here, notice this could be anything. This n could be any value. So if I take the next one, it'll be bigger than the previous one. Thus, the sequence of partial sums S sub 2n is increasing. And since it's increasing, we can say it's monotonic. At this point, you may see where we're going with this. We've shown it's monotonic. If we can now show that it's bounded, well, then it's bounded and monotonic, and therefore must converge. All right, so let's go ahead and look at the second part. So now let's go ahead and go back to our partial sums. And here, I started off by grouping this one with that one, and then this one with that one. But I don't have to group it that way. After all, I could say S sub 2n is equal to, and remember, addition and subtraction is associative as long as you keep the same signs, as long as positives and negatives don't get mixed. So here, instead of writing it with these two together and then these two together, let me start off with a sub 1 on its own. And now let me say minus a sub 2 minus a sub 3. Notice that's still the same thing, right? That's a sub 1 minus a sub 2. Double negative would make that plus a sub 3. And then I could do that for the next set of terms. I could say minus a4 minus a5 minus, and dot, dot, dot. Right? This still says the same as the line above it. And then eventually we're going to get to, eventually we're going to get last two. Well, since this one doesn't have a partner, the one at the very end won't have a partner either. So we'll say this is minus 2 sub 2n minus 2 minus 2 sub 2n minus 1. And then the very, very last one is just going to be minus a sub 2n. Oh, I don't know why I wrote that as a 2. That should be an a, shouldn't it? There we go. Okay. Take a moment and convince yourself that this is the same as our original expression up here. You can distribute these negatives and see that it does work out exactly the same as the original line. Okay. Notice now that these are positive for the exact same reason that we had up here. Since this is a decreasing sequence, the a sub n's are decreasing by this condition here, then that means that a sub 3 is less than a sub 2, which implies that a sub 2 minus a sub 3 must be positive. Okay, so if that's positive, here I'm subtracting a number, and here I'm subtracting another number, and I'm subtracting another and another and another, and at the very end I subtract another number. So here all of these are positive for the same reason that this one was. Okay, but now if I'm subtracting every time, well, that means a sub 1 was the biggest thing I ever had. And from then on, I started to subtract stuff every single time, which means that S sub 2n is bounded by a sub 1. This will never get any bigger than a sub 1. So S sub 2n is bounded above by a sub 1, just like that. But now we have a function that is monotonically increasing, and it's bounded above. Right? You can imagine a quick visual of that. You have a function that is, and we talked about boundedness and monotonicity in 9.1, but let's just remind ourselves of that. You have a function that's constantly increasing, or rather a series that's constantly increasing. a sequence. It's constantly increasing, but it's bounded above. So it's got to keep going up, but it can't go past that line. Oh, so then it has no choice but to approach that line asymptotically. Oh, well then that means that this sequence will converge to this number. Oh, okay, so then that means that S sub 2n will converge to A sub 1, right? Well, no, not necessarily. Because again, here we know that it's bounded above by that number. We don't know that that's the best number that we could bound it by. Maybe A sub 1 is higher than what it converges to. So here, we can't say that S sub 2n will converge to A sub 1. Because we know A sub 1 is up here. We just don't know that it's the one that gets the closest to this sequence. Maybe there's one slightly closer to it. So unfortunately, we can't say this converges to that, but we can definitely say that it converges. So here we say S sub 2n is bounded above and monotonically increasing so it must converge. But now you say, well, wait a minute. You looked at the even partial sums. Can you do that? I thought you were supposed to look at all the partial sums. Well, that's true. Here we've only looked at the even partial sums. But it turns out that the odd partial sums are going to behave the same way, and it's really, really easy to show that. All we have to do is get rid of one term. Because if this is an even term, right, an even number of terms, sorry, then if I just get rid of one, well, then that even number of terms becomes an odd number of terms. So let's just go ahead and strip one of our terms away. Notice right here that S sub 2n, well, that's this entire sequence right here. Oh, sorry, I keep saying sequence, series. That's this entire series right here. Okay, well, notice that's the same as our S sub 2n minus 1. In other words, if I stopped one short, it would give me all the same terms except for that one. So if I took S sub 2n minus 1, which is this, and I subtracted that one number, it would give me S sub 2n. Let me write that. If I started off with S sub 2n minus 1, and I just subtracted that one last number, that would give me my S sub 2n. Okay? And here, let's go and convince ourselves of that before we continue. From here, from the very first term up to the 2n minus first term, that's S sub 2n minus 1. Now, if I just subtract that one extra term, and that should be a 2n right here, if all of this is the sum, S sub 2n minus 1, all I have to do is subtract that one last term, and then I get back my S sub 2n. So if I subtract that one term, I get back my S sub 2n. Okay, but we know that this converges. We just showed that. But we also know, based off our conditions, that this A sub 2n will approach 0. After all, that's one of the conditions of our theorem. So far, we've dealt with entirely this condition, the fact that our sequence of terms, our A sub n's, is decreasing. But now let's go ahead and deal with this condition. The limit as n approaches infinity of A sub n approaches 0. So if this gets any bigger, this will approach 0. All right, well, what that means is that if I make this approach infinity, this whole thing will approach 0. Let's write that out. Since the limit as n approaches infinity of A sub 2n is equal to 0, then that means that if I take the limit as n approaches infinity of this side, that's the same as taking the limit as s approaches infinity of that side. Okay, so limit as s sub 2n is equal to the limit as n approaches infinity of s sub 2n minus 1 minus a sub 2n. Okay, limit of this side is equal to limit of that side. But since this limit exists and is equal to and it's going to 0, we can write this as the limit as n approaches infinity of s sub 2n minus 1 minus the limit as n approaches infinity of a sub n or I guess I'll write that as s sub 2n, which, as we see, approaches 0. And since that's going to 0, that means these two limits are equal to each other. So here the limit as n approaches infinity of s sub 2n is the same as the limit as n approaches infinity of s sub 2n minus 1. What that means is it doesn't matter if you have the even partial sums or if you have the odd partial sums, they both do the same thing. They both go to the same limit. So what that means is that it doesn't matter if you have the even or the odd ones. So that means it's going to be true for all of them. So the limit as n approaches infinity of s sub n, right here, it doesn't matter if n is even or odd, so we don't have to distinguish them. We can just say n. This must converge. Oh, but now that means that the nth term of our sequence of partial sums converges, and therefore by definition the sum as I goes from 1 to n of minus 1 to the n plus 1 of a sub n must converge. All right? By definition, if the partial sums converge, that means the total series must converge. That's the definition of what it means for a series to converge. And that concludes our proof, because now we know that as long as we have those two conditions, namely the fact that the limit of the nth term approaches 0 and that your terms be decreasing right here, as long as you have those two conditions, that's sufficient to show that your infinite series of alternating terms must converge. And that concludes our proof. To show that an alternating series converges is almost trivial, because all you really have to do is confirm that the limit of the nth term approaches 0. All right? So let's take a look at an example of that. Let's say we have the sum from n goes from 1 to infinity of minus 1 to the power n over n. As n goes from 1 to infinity of negative 1 to the power n over n. Now at this point you might say, well, that looks like the harmonic series, 1 over n. And we saw in the previous section about p series that wouldn't converge. Well, that's true. The harmonic series, the p series with p equals to 1, does not converge. But that's not what this is. This is not the harmonic series, because the harmonic series doesn't alternate. So here the question is simply, does this converge? Now remember, even though this is technically a yes or no question, answering yes or no is not sufficient. We say yes, it converges because of the following results of the following test. Or no, it doesn't converge, it diverges because of the following results of this test. So here, does this converge? All right. First of all, we notice this is an alternating series. And what makes this an alternating series, let me write this a slightly different way. You don't really ever have to write it this way, but I'm going to do it just to compare it with our definition. So here, this can be written as, I'm going to separate this part from the rest. I can write that as minus 1 to the power n times 1 over n, which is definitely that one. All right, the sum as I goes from 1 to infinity of minus 1 to the n, minus 1 to the n times a sub n. Okay, so here we have to confirm 3 different things. You say 3? I thought there was 2. Well, there are 2 conditions, but then there's one last thing. Here, we do need our a sub n's to be positive. It's usually very simple to show that, but here, there are 3 things to confirm. We have to know that our a sub n's are all positive, and we have to know that our a sub n's approach 0, and we have to show that they're decreasing in size. Okay, so because it's an alternating series, the nice thing about alternating series is that they come with their own test. First of all, we have to check, is a sub n greater than 0? Okay, well, that's 1 over n. Keep in mind, n is starting from 1 to infinity. So yes, absolutely, that's positive. That's positive, trivially so. For all n greater than or equal to 1 over n is greater than 0. Yeah, you're taking a positive number and you're taking its reciprocal. Of course, that's greater than 0. Okay, so that one's trivial, and it always will be. There's never really any difficulty there. Same thing if it's not true. If it's negative, it'll be fairly obviously negative. Okay. The second condition. Now, these do require some work sometimes. The second condition is we want to show that the limit as n approaches infinity of our a sub n is going to go to 0. Okay. All right, well, let's see that. Here's our a sub n, so let's consider its limit. The limit as n approaches infinity of 1 over n, well, yeah, that's a Cal 1 thing, right? That's going to go to 0. If you have 1 over a power of x and x is going to 0, the whole thing goes to infinity. But if x is going to infinity, then the whole limit goes to 0. Yeah, just like that. This is something that can be stated without any kind of proof or confirmation. This is a matter of fact from Cal 1. At this point, I expect you guys that, everyone here would know that, and I wouldn't really require you to prove that. It's just, oh yeah, that's just a thing we know. It's just like 2 plus 2 is 4. No one proves that anymore. Okay. And then 3, we also have to confirm that our terms are decreasing. So our a sub n minus 1, let's say a sub n plus 1, makes our notation a little simpler. The next term must be less than our previous term. That's what it means for a function to be decreasing. The bigger term is less than, the subsequent term, the one that happens later, is less than the earlier term, the one that happened earlier. Okay, well, let's go and compare that. Here, I'm looking at the a sub n plus 1 term. That's going to be 1 over n plus 1. And over here, the nth term is just going to be 1 over n. And so here, this has a bigger denominator, which means it must be smaller overall. And there we go. So we've confirmed all 3 conditions. Our terms are positive, go to 0, and are decreasing, monotonically decreasing. So that means that, yes, this series converges. The series converges as it satisfies all conditions for, I just misspelled the word for. That's impressive, isn't it? All conditions for a convergent alternating series. All right. Now, there is one thing to say about these conditions. If all 3 of them are met, we know for a fact that it will converge, because that's what the alternating theorem tests, alternating series test tells us. We say, okay, but what if one of these doesn't work? What if we don't satisfy these? Does that mean that my series diverges? Depends which one. Okay, so let's say this one fails. If we fail to show that a sub n is greater than 0, let's say some of these terms actually are negative, right here. That doesn't mean that this thing doesn't converge. You say, so it does converge? No. If this is not greater than 0, that means we don't have an alternating series. So this would be the wrong test to use anyway. So here, if this is not greater than 0, it doesn't mean that this converges. It doesn't mean that it diverges. It means we have to find some other test because it's not really an alternating series. So here, let's go ahead and make a note of that over here. What if one of the conditions of the alternating series test fails? It depends which one. So let's say the one that fails is a sub n is not greater than 0. If that's what happens, then this is not really an alternating series. Which means you don't learn anything about it, whether it converges or diverges, but rather you have to go find another test. So can't use the alternating series test. Go find another one. And there are going to be plenty of other tests. Okay? All right, so what if the second condition is the one that fails? What if we get that the limit as n approaches infinity of our a sub n's does not approach 0? Then your series diverges. And you say, oh, because it failed the alternating series test? No, because it failed the nth term test. Remember the nth term test all the way back in section 9.2 tells us that if the nth term of a sequence doesn't approach 0, then it can't possibly converge. That has nothing to do with whether or not it's alternating. So here, if the limit as n approaches infinity of a sub n is not equal to 0, the series diverges, and you don't even mention the alternating series test. It diverges due to the nth term test. Okay. The third one, if your a sub n plus 1 is not less than a sub n, then you don't learn anything. You have to go find another test. We don't know. We have to go find another test. It is possible for an alternating series that isn't decreasing to converge, right? Without giving any explicit function, let's just take a look at a quick illustration to show that. Here we have an alternating series where our terms aren't strictly going to be less than. So you might have some where 2 of them in a row are the same value, and then 2 in a row are the same value, and then 1 up, and then 1 down, and then 2 up, and then 2 down, like this. And still, eventually, you're going to have them converge to a single value. So here, we don't strictly have a monotonically decreasing function. A monotonically decreasing sequence of terms that we're adding together. So, but we still have convergence. Oh, but this was a condition that guaranteed that the alternating series would converge. Okay, so if we don't have that, we can't guarantee that it works, but there are instances where it does. So if the third condition is the one that fails, we don't know. So you have to go find a different test. Now, notice that we just saw an example of a convergent alternating series that really looked like the harmonic series. So there's something about the alternating nature of this series that makes it a little more forgiving, that makes it a little more manageable than the harmonic series. We saw that in a previous section, if you take away this -1 to the n, and you just leave that series, sum as n goes from 1 to infinity of 1 over n, that will diverge. But by making the terms not the original form, but by having them alternate, all of a sudden our series will converge. So some series can be made to converge. Now, they're different series, obviously, because one converges and one doesn't, but this extra factor can temper the size of these to make them converge. So there is a difference between whether or not a series converges in its own right and as an alternating series. So with an alternating series, we're going to see 2 different kinds of convergence. Not that convergence means something else, but we're going to say, okay, did it converge under its own power, for lack of a different term here, or did it converge strictly because we had alternating terms? This brings us to the difference between absolute convergence and conditional convergence. So let's go ahead and define these things. Well, actually, I suppose I'm getting ahead of myself. Let's give a theorem first, and that theorem will motivate the definition. So our theorem is And this will motivate very heavily how we define what we're going to define here in a moment. Let's talk about absolute convergence. What absolute convergence says is, let's start off with a series. If you can take the absolute value of the terms of that series and still let it converge, then that means that that series converged because of its terms and not because of its signs. A little more formally, we say let S be the series, the infinite series, given by the sum as n goes from 1 up to infinity of a sub n, be a series. If the sum as n goes from 1 to infinity of the absolute value of a sub n converges, then S also converges. In fact, here, let me just write it this way. Then the sum as n goes from 1 to infinity of a sub n also converges. Just like that. This is called absolute convergence. Absolute because of the absolute values here. If you can take the absolute value of each term and have that new series converge, that guarantees that your original series must also converge. And the proof of this, okay, so begin by assuming that this series of absolute values of terms converges. Assume that the sum as n goes from 1 to infinity of the absolute value of a sub n converges. Okay, assuming that that converges, now consider the following. Well, note that if I were to take a sub n without absolute values and add to that the absolute value of a sub n, that's got to be positive, right? Or like this. Because of course, if these are both positive, well, they're going to add together. And if one's a positive, well, then the other, and if one is negative, well, then this one must be positive. And so they would cancel each other out. So I guess I should say greater than or equal to. Okay. If this is positive, then this one's also positive, and they add together to give me a positive. If this one's negative, this one's positive, and they cancel each other out. Notice that the biggest that these can get is going to be double the absolute value of an. Because again, if this is positive, then so is that, and they add together, which gives me double the amount. But if this one's negative, well, then they don't add together. They cancel each other out, and so I get either this or something less than this. Okay, so now let's go ahead and consider a series of terms that look like this. The sum as n goes from 1 to infinity of a sub n plus the absolute value of a sub n must be less than or equal to the sum as n goes from 1 to infinity of double the absolute value of a sub n. Okay, if these terms are less than these terms, then the sum of these terms must be less than the sum of these terms, less than or equal to. Oh, but that's a common factor, which we can factor out. So this is the sum as n goes from 1 to infinity. Here, I'm going to leave the 2 out here, of the absolute value of a sub n. Oh, but we know this converges. And in fact, let me say over here, this converges to some number L. Oh, okay, well then that's got to converge to L, and that's 2. So that's going to be 2L. Oh, okay, so this series is less than something that converges. That's a direct comparison test. Thus, the sum as n goes from 1 to infinity of a sub n plus the absolute value of a sub n converges by the direct comparison test. Right? You're less than something that's finite, you must also be finite. You're smaller than something that's small, oh, then you must be small also. Okay? So this converges by the direct comparison test. But now, notice that if I subtract these two, if I subtract these two, look what happens. But I can take the two series, the one that I assumed converged and the one that I just found, and I can subtract them. The sum as n goes from 1 to infinity of a sub n plus the absolute value of a sub n minus, well, here, let me write it this way, minus a sub n. That's going to, well, here, let me not skip that step. So notice that a sub n plus the absolute value of a sub n minus the absolute value of a sub n is equal to a sub n. So if I take the sum of these terms, that's the same as taking the sum of these terms. So take the sum as n goes from 1 to infinity of a sub n plus absolute value of a sub n. Here, I'm going to go ahead and write this as minus the sum as n goes from 1 to infinity of a sub n, absolute value. That's equal to the sum as n goes from 1 to infinity of a sub n. The sum of these terms is the sum of these terms. But since these are all just sums and differences, linearity takes effect, and I'm allowed to separate these. Right? I can take this sum, separately take this sum, and then subtract. And this is just linearity at work. But we know this converges because we just saw it. That was the one that we just finished proving that it converges by the direct comparison test. And we know that this one converges by assumption. We began by assuming that converges. So over here, this converges by a direct comparison. And this converges by assumption. We began by assuming that was true. Oh, but this must equal to the difference of these two. Oh, but this is going to equal some number minus this is going to equal some other number. And if I subtract those two numbers, I get a number. Oh, that must mean that this sum converges to that number. So the sum as n goes from 1 to infinity of a sub n converges. So what that does is it shows us that if the absolute value of the terms gives me a series that converges, then the original series must converge as well. Now, the other way around is not true. If these terms converge on their own, taking their absolute value might lead you to something that doesn't converge. Saying that one more time, if the sum of absolute values converges, the sum without the absolute values must also converge. But if the sum without absolute values does not converge, if the sum of absolute values let me say that again. If the sum without absolute values converges, that doesn't mean that the sum with the absolute values has to converge. This one converging means that one converges. This one converging doesn't tell you anything about this one. So be careful with the direction of that statement. This brings us to the difference between absolute convergence, which we just defined using this theorem, and conditional convergence. So let's go ahead and define this. Let's begin with a series. The sum of a sub n's. If the series, let me not say it that way. Let's just say it this way. The series sum as n goes from 1 to infinity. Here, this doesn't have to start at 1. It could start anywhere, but by default, we start at 1. The series n starts from 1 to infinity of a sub n is said to be absolutely convergent. If the sum as n goes from 1 to infinity of absolute value of a sub n is convergent. On the other hand, the series sum as n goes from 1 to infinity of a sub n is said to be conditionally convergent. If the sum as n goes from 1 to infinity of a sub n converges, but the sum as n goes from 1 to infinity of the absolute value of a sub n diverges. So absolute convergence is said to be the stronger of the two, meaning it implies the other one. If something is absolutely convergent, then it means it's also convergent in the original form. All right? However, conditional convergence is considered weaker, meaning, oh, you can have one without the other. That's what we mean by something being stronger or weaker in math. If something is stronger, that means it automatically implies something else. If something is weaker, that means it only implies itself, not anything else. This might be a little bit hard to wrap your mind around at first, but a nice example of this will show exactly what this means. So consider the following series. And the question is just, is this series convergent? Is this convergent? And the series is going to be the sum as n goes from 1 to infinity of negative 1 to the power n minus 1, or I guess I should say plus 1. Negative 1 to the power 2n plus 1 over n square root of n. Okay, whenever you're looking at an alternating series, this is the time to consider absolute versus conditional convergence. It's not that it doesn't apply other times, it's just that other times your terms are usually already positive. Think about the geometric series, think about the harmonic series, think about the telescoping series, think about most of the series that we've seen so far. For the most part, our terms are usually positive. Or if they're not positive, the negative ones are canceling the positive ones in the case of the telescoping series. So the absolute convergence, I suppose you could talk about it, but the negatives are either not there to begin with, so the absolute value wouldn't do anything, or they're there for a reason. They're there to help cancel out some other terms, and in which case taking the absolute value would give you a different kind of series, which would be a little harder to work with, in particular the case of the telescoping series. But when you have a alternating series, that's the time when we really want to consider absolute versus conditional convergence. Start by considering absolute convergence. It's the stronger of the two. If it's absolutely convergent, that means you're done, because that automatically implies everything else is convergent. If you try for absolute convergence and you don't get it, that's when you try for conditional convergence. So first, let's try for absolute convergence. All right, so let me take the sum as n goes from 1 to infinity of the absolute value of negative 1 to the power n plus 1 over n square root of n. Notice the absolute value, all it does is it completely wipes out any instances of a negative. So here, these are unaffected, but this minus 1 to a power, just completely ignore it. So this is really the sum as n goes from 1 to infinity of 1 over n root n. Oh, but now that one's nice. Because notice, n times square root of n, that's the sum of 1 over n to the 3 halves. That's 1 half, and when I multiply them together, I add their powers. Power 1 plus power 1 half gives me power 3 halves. But that's a p-series. This is a convergent p-series. And how do I know it's convergent? Magic, right? No, we know it's convergent because p, 3 halves, is greater than 1. Well, okay, maybe it's magic. I don't know. Just like that. So, we know this converges. Oh, but these were the absolute value of these terms. Oh, so by taking the absolute value, I get something that converges. Oh, so that means that my original series is absolutely convergent, which means that, oh, well, if this one converges, that automatically means this one's convergent. And it was convergent because taking its absolute value gives you this p-series. So the way we state that is the sum as n goes from 1 to infinity of minus 1 to the power n plus 1 over n root n is absolutely convergent. And we're done. We don't try to test the other kind of convergence because remember, this is the stronger one. If something is absolutely convergent, then it's convergent every other way as well. So here we would stop. And by saying it's absolutely convergent, anyone reading it automatically knows that every other kind of convergence works as well. Okay? Now, what if it's not absolutely convergent? Oh, well then you can test if it's conditionally convergent. So we always start with the stronger of the two to see if that gets us anywhere. But if not, well, then we test the weaker one. So for the next example, go ahead and consider the sum as n goes from 1 to infinity of minus 1 to the power n over the square root of n. Okay? Once again, start by testing for absolute convergence. So we're going to take the absolute value of the nth term and then see what happens. All right. So consider the series sum as n goes from 1 to infinity of the absolute value of minus 1 to the n over square root of n. Okay. And in this case, go ahead and you should maybe try that. Go ahead and pause the video and see if you can determine whether or not this converges. Once you have an answer, go ahead and unpause the video and we go through it together. All right, so by taking the absolute values, that means minus 1 to the n. Well, this term is always either positive 1 or negative 1. But when you take the absolute values, that just always stays positive 1. These were already positive, right? 1, 2, 3, 4, 5 out to infinity. So these are not affected by the absolute values. So this just gives me the sum as n goes from 1 to infinity of 1 over square root of n, which is the same as the sum as n goes from 1 to infinity of 1 over n to the 1/2, which is a p-series. And since p is 1/2, it diverges. This is a divergent p-series. Since p is equal to 1/2, which is definitely less than 1. Okay, so then that means that my series is not absolutely convergent. Now that doesn't mean we're done. That just means we don't have the stronger form of convergence. We might still have the weaker one. So my series is not absolutely convergent. Now, because it's not absolutely convergent, we might have to settle, for quote unquote, we might have to settle for a weaker form of convergence. So now let's test for conditional convergence. And you say, well, how do I test for conditional convergence? Well, note, if I'm looking for absolute convergence, I'm taking the absolute values, which wipes out this term. But if I'm looking for conditional convergence, that means I'm not taking the absolute values, which means this term stays here. Oh, but if the term stays here, then that's an alternating series. So let me use the alternating series test. And in the alternating series test, I have three things that I have to check for. I have to check that a sub n is greater than 0. All right, well, that's clearly true because here our a sub n is 1 over root n, right? The a sub n is what you get when you ignore this term. If you ignore this part, you just get 1 over root n. And since n is a number from 1 to infinity, that is most certainly positive. Okay, so our first condition is met. The second condition is that the limit as n approaches infinity of our a sub n's should equal to 0. All right, let's see what happens there. Well, I want to take the limit as n approaches infinity of 1 over the square root of n. Or in other words, I want to take the limit as n approaches infinity of 1 over a power of n, which we remember from Cal 1 is most certainly 0. And finally, we have to check that these are decreasing. We want to make sure that a sub n plus 1 is less than a sub n. Well, let's see. A sub n plus 1 is 1 over the square root of n plus 1. A sub n is 1 over the square root of n. Oh, these are identical except for that extra constant in my denominator. Oh, so that means that this has a bigger denominator than this one. So that means overall, since it has a bigger denominator, it must be smaller. Oh yeah, that's what we wanted. The n plus first term is less than the nth term. So that does meet all three conditions. So even though our series was not absolutely convergent, we can say that the sum as n goes from 1 to infinity of minus 1 to the n over the square root of n, this is conditionally convergent. Meaning it's convergent on the condition that we leave it as an alternating series. If we remove that and leave just the absolute value of the terms, then it's no longer convergent. So this is conditionally convergent. Just like that. Finally, let's go ahead and state something here. Without any proof, we're going to state a theorem. For the most part, it's difficult to know what a series converges to. Most of our tests, with one or two exceptions, will tell us whether or not a series converges without actually telling us what it converges to. That's because finding what a series converges to can be very, very difficult, a lot more than what we can do in a calculus class. It requires a lot more. However, some of the tests do allow us to find what it converges to. With an alternating series, we can estimate what our series will converge to. All right? So the theorem doesn't actually allow us to determine what our series converges to, but we can get a very, very good estimate. So let's start off with a alternating series. Let S be the sum n goes from 1 to infinity of minus 1 to the power n times a sub n, or we can do it the other way, the sum as n goes from 1 to infinity of minus 1 to the power n plus 1 times a sub n. Either one's fine. It doesn't matter if you start with a positive term or a negative term. All that matters is that you have an alternating series that converges. So let's let that be a convergent alternating series such that a sub n is less than or equal to a sub n plus 1. Oh, I have that backwards, don't I? It should be such that a sub n plus 1 is less than a sub n. We want that to be decreasing. Okay? Then the absolute value of s minus s sub n, where s sub n is the nth partial sum of s, and here let's go ahead and label that. Let's just start it this way, where s sub n is the nth partial sum of s is such that the absolute value of s minus s sub n is less than or equal to a sub n plus 1. Okay? That might sound a little strange, but if we dissect it, it actually says something very, very simple. What it says is start off with an alternating series and have it be such that the terms are decreasing. Now, we know this. This is we've seen this as one of the conditions for convergence of an alternating series. So whenever we have one of these that converges, we know that's going to be true. Okay, but we want to highlight that. That tends to be very important here. Then, if you take what this actually converges to, if you take the full sum from 1 to infinity, and you subtract away the sum of the first n partial sums, then that difference is less than the n plus first term. Notice what that's saying. This is just an estimate. This is me adding together the first 10 terms. This is the sum from 1 to infinity. This is the actual thing it converges to. If I take the difference between the estimate and the real answer, that estimate has to be less than the n plus first term. So if I estimated it using 10 terms, then if I just look at the 11th term, I know that the real answer must be within that much of the estimate. So consider an example of that. Let's approximate the sum of the convergent alternating series. Here, they're telling you, oh, this is convergent. We guarantee you. We tested it for you. If they didn't tell you that, it would be up to you to test it first. Because, of course, if it doesn't converge, well, then you can't find what it converges to. You first normally have to test whether or not it converges. But in this case, they've already done that for you. So approximate the sum of the convergent alternating series that's given by the sum as n goes from 1 to infinity of minus 1 to the power n over n factorial. Remember how factorials work? Take that number, count down to 1, and multiply the numbers together. So 5 factorial will be 5 times 4 times 3 times 2 times 1. Okay? And we're going to estimate it so that it has an error that's less than 0.001 to within 0.001. All right, so in order to do this, I'm going to write out the terms the long way. Instead of writing it in summation notation, I'm just going to start writing out some terms. So that's going to be minus 1 to the power 1. And here, let me actually just write it this way. Over 1 factorial. Plus negative 1 to the power 2 over 2 factorial. Negative 1 to the power 3 over 3 factorial. Negative 1 to the power 4 over 4 factorial. Negative 1 to the power 5 over 5 factorial. Plus dot, dot, dot. Okay. All right, now here, let me go ahead and clean that up. Negative 1 to the power 1, that's negative 1 over, that's just the number 1. Plus, that's positive 1 now. 2 factorial is 2. Now, that's a minus 1 now, so let's go and write that as minus 1 over 3 factorial is 6. And now that's positive, so that's going to be plus 1 over 4 factorial, which is 24. And now that's a negative, so minus 1 over 5 factorial is 120. Like that. And let's see what we have. All right. If I were to approximate using the first two terms, what my theorem tells me is that my error would be this much. All right, well, I'm trying to do it to a decimal here. So that's going to be what? That's 1,000th. So what I want to do is, all right, if I approximate using these terms, that's my error. Oh, yeah, but that's bigger than this. Here we're doing it in absolute value, right? Our absolute value is less than a certain amount. So here we don't worry about the plus or the minus. All we're looking at is the number. So if I approximate using these, the number here, we're not worried about the plus or minus. We're just worried about the a sub n. That doesn't include the minus 1 to the power n. My error is 1/6, which is too big because I want it to be 1/1000. Okay. If I approximated using the first three terms, that's my error. Oh, but that's still too big. If I approximate using the first four terms, that's my error. Forget about the minus, just the 1 over 120. Oh, but that's still too big. 1 over 120 is bigger than 1 over 1,000. So here I need a few more terms. Okay, so let's get a few more terms. Minus 1 to the power 6 over 6 factorial, minus 1 to the power 7 over 7 factorial, plus dot, dot, dot. Let's see if that's enough. If I take 6 factorial, that's, let's see, that's 720. Minus 1 to the power 6, that's a positive 1. And now negative 1 to the 7 is negative 1 over 7 factorial, which is 50, 40. There we go. Of course, these terms do keep on going, but we finally found a term that is less than the error we wanted. Okay, so this is the first term, a sub n, which is equal to 1 over 50, 40, which is less than the error we wanted. Okay? All of these are much bigger than the error we wanted. This is the first a sub n that you see that's less than. Remember, a sub n doesn't count the sign. It only counts the number. So here we're just looking at the 1 over 50, 40, not the negative part, just the number. Okay, so since this is the very first term that has less than that amount of error, that means that if I add together these terms, that's going to give me the sum of this to within that much error. So let's go ahead and add those all together now, which when I add them together gives me negative 91 over 144. Wasn't about to do that one in my head. That was just a little too long for my taste. So that one's going to be equal to negative 91 over 144. And you say, oh yeah, but that's not really what your series converges to, right? Well, no, it doesn't. What the theorem says is if I use these terms, this is correct to within this amount. So whenever we write our answer, we would write, okay, this is what our series converges to. Here, let me write this as S equals. So here, S is equal to that amount. But that's not quite right. My answer could be slightly more or slightly less than this. Okay, well, that's my error. So I could say plus or minus 1 over 50, 40. So in other words, that's my answer, plus or minus this little tolerance. So my answer could be as big as this plus 1 over 540, or it could be as small as this minus 1 over 540, or 50, 40. All right? So here that means that my answer S is somewhere between negative 91 over 144 plus that amount and negative 91 over 144 minus that amount. This is just for your edification to show you exactly what that means. But here, this would be the correct estimate. All right? Approximate the sum of the convergent series to within 0.001. Oh, here's your estimate and your error. In fact, let me even label that. That's your estimate, and that's your error. And the way that works is that means that this, we know it converges. We were told that it converges, and if we weren't told, we could always test it ourselves. And because it converges, it must converge to something. The number that this converges to is somewhere between here and here. And so that brings us to the end of our section. For an assignment for the section, go ahead and try problems. Oh, let's do this. Section 9.5. Do numbers 9 through 25 odd, and then we're going to skip a few here, and then try 31 through 53 odd, and that'll suffice. If anybody has any questions, please write them down and make sure you let me know. I hope you'll have a nice day.